Hi, welcome to my final lab presentation where we discuss Faraday's law. This lab investigates the interaction between a foil wrap and a falling magnet. The experimenter is expected to record the average time taken for the magnet to fall and compare the experimental value to that of the computational value. This lab will require the students' understanding and use of Faraday's law and Newton's law of motion to solve the problem being asked. By the end of the experimenter should have determined the average time taken for the magnet to fall through the aluminum foil, modeled interactions between the magnet and the foil on glow script, and compared the computational results and data found. This lab involves the use of the following key concepts: view of Savart law and magnetic field of a dipole magnet, magnetic flux, Faraday's law, and Newton's law of motion. This slide pictorially describes the system. Upon falling, the magnet experiences two different forces: the gravitational force and the magnetic force. The magnetic force originates from an induced current formed from the magnetic field from the dipole that acts on the aluminum foil paper. Upon conducting the experiment, the following data was found, and then by taking several trials, we found that the average time taken for the magnet to fall through the aluminum foil is 0.215 seconds. After taking experimental values, we moved to coding. The first steps were to put down the physical constants, to initialize the graph, and then to create the aluminum foil tube. Afterwards, we created the bar magnet and we visualized the bar with its qualities. We also put down our initial conditions for the bar magnet's velocity and the time being 0. This was useful especially for the iteration used later. Before iterating, however, we had to make the function. The first function was used to find the B field from the dipole, which we used from the magnetic field equation of a dipole. And then we used the flux equation that was provided to us and derived by using Faraday's law. After creating the functions, we use a while loop and a for loop to update the position and the velocity of the magnet as it fell through the aluminum foil, where we finally have our pictorial result shown here, showing that the velocity gradually decreased as it fell through the aluminum foil, and coming up with a computational time of 0.227 seconds. Now the following questions were asked. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity were to approach 0, then the current would increase in value. Hence, the force acting on the magnet would grow larger as resistivity decreased, and one would expect the magnet to take a longer time to fall through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes were cut through the tube at certain intervals, the whole rings would experience no current. Now there are two sets of errors that likely occurred during this lab. Firstly, the experimental portion was done in an area away from metallic objects and electrical equipment. Also, we had to use aluminum foil because using any ferrous material would make the experiment void. The magnet would be attracted to any ferrous material. However, upon videoing and scrubbing the video to find the times, there's a slight parallax error during the scrubbing process. Furthermore, there is an error in the code because it is very unlikely that the velocity of the falling magnet would have a constant gradient, which implies that it had a constant force. This is unlikely because magnetic force would have to change over time. And as a result, there has to be a change in acceleration, and the gradient of the velocity time graph cannot be constant. Despite all errors, however, we ended up having an experimental value of 0.215 seconds and a computational time of 0.227 seconds, with an overall percentage error of 5.29%. Thank you.